So the first question we have, A1, is let T be a linear transformation from R2 to R be is T surjective? So with it being a linear transformation, we have that the dim of V is greater than the dim dimension of W. This implies that it's not injective, but it doesn't tell us anything about surjective. It means it could be surjective or could not be surjective. So this is sometimes. Sometimes surjective. We can have T of xy equaling x. That is surjective. And we can have T of xy equaling 0. And that is not surjective. So sometimes we're surjective. Now we have, for A2, we're looking at alpha, T alpha beta. Remember, beta is used when we're looking at the coordinate vector for TV of beta. And beta tells us how many entries are in TV of beta. The number of entries is the number of basis vectors. So if we look in each of our columns, that's going to be TV1 beta, where V1 is in alpha. And because it has 3 entries, that tells us that the dimension of W equals 3. Now, this corresponds to TV1. This is TV2, so on and so forth. And alpha is the set V1 through Vn. So the number of columns that I have tells me the number of vectors in alpha. So, and remember that alpha is a basis and the dimension is the number of vectors. So because I have 4 columns, the dimension of V equals 4. Next, we have a linear transformation from V to W, where V and W are finite dimensional vector spaces. If T is surjective, what can we say about the rank of T? So the rank of T is the dimension of the image of T. Now, because it's surjective, we had that the dimension of, we are surjective if and only if the dimension of the image of T equals the dimension W. So that's the first thing that we can say. And then because it's surjective, there's other things we can say. We can say that the rank sorry, this is what we can say. We can say that the rank of T equals the dimension W. We can also say that the dimension of V is greater than or equal to the dimension W, because we know we're surjective. But this is kind of our main idea. If you said this, and if you had replaced this with the dimension of V is greater than or equal to the rank of T, that also would be accepted, because that gives us information about the rank. Okay. Next, we have a matrix multiplication. This question is asking us, do we know how to multiply matrices, and do we know how to compute complex numbers? So here, our matrix product is going to result in 2 times 3 plus 2 minus I times 2. Then it's going to be 2 times 4I and plus 2 minus I times 0. Then it's going to be 2 times 3 plus 4I times 2 and 2 times 4I plus 4I times 0. Simplifying this, we get 6 plus 2 minus 2I, or 6 plus 4 minus 2I, 8I 6 plus 8i and 8i, which equals 10 minus 2i, 8i, 6 plus 8i, and 8i. Assuming I've made no multiplication errors. So a question like this is purely, can you do this computation? Can you work with your complex numbers? Do you know how to do matrix multiplication? Next, we have a linear transformation, and they tell us what t of E1 and t of E2 is. So what we need to do is we need to take t of 1, 3, and this is equal to t of 1 times 1, 0, plus 3 times 0, 1, which equals t of 1E1 plus 3E2, which is equal to 1TE1 plus 3TE2, which equals 1 times 1 minus 2, 5, minus 5, plus 3 times minus 2, 4, 3, which is equal to minus 5, 10, 4. As long as I haven't made any math errors. For these two questions here, the way that it's typically graded is half a mark for you clearly know the process and half a mark for no calculation errors. So if you are doing your calculations and you get 1 or 2 small math errors, but you show you know what you're doing, you get a half a mark. You get it completely correct, you get a full mark. Typically is how those are graded. Big thing we want to know is, do you know the process and can you compute? Next, we have a true or false. We have if the dimension of n is v and then v has exactly one subspace w naught that equals v. Yes, this is true. This was one of the theorems that you guys did in your tutorial worksheets. It also has one such that the dimension of w naught equals 0. And this here, w naught equals v, and here, w naught equals the set containing the 0 vector. So there's only one subspace with the same dimension as the original subspace, given it's finite, and there's only one subspace with the dimension being 0. Okay, next we have our dimension of linear transformations. Well, this is 4 times, and the dimension of this is 2 times 3. To calculate the dimension of linear transformations that go from the polynomials of degree at most 3 and the real 2 by 3 matrices, we take the dimension of each. So this is 4 and this is 6, and we multiply them. So we take the product of those dimensions. If we think of it, we can think of it as the matrix where our input is 4 and our output is 6. And how many entries are in this matrix? And if we were to count it, we would get 24. Okay. So our matrix representations would have 4 columns and 6 rows, totaling 24 entries. Now we have a linear transformation from P5 to 3, and it's asking what are all the possible values for the nullity of T. So here we've got the rank nullity theorem, which tells us that the rank of T plus the nullity T equals the dimension of V. So here, the rank is bounded by W. So we have the constraint that the rank of T is less than or equal to the dimension of W. So if I know that the dimension of V is 6, and I know that the rank of T is less than or equal to, here the dimension is 3, I know that the rank equals 0, 0, or 1, or 2, or 3. So by plugging each of those numbers in, I can get my nullity. So my nullity is, if I plug in 0, that gives me 6. If I plug in 1, that gives me 5. If I plug in 2, that gives me, or 2, that gives me 4. And if I plug in 3, that gives me 3. So it's 3, 4, 5, or 6. Next, we have a basis for p degree 4. This is, do you know the quote unquote standard basis for polynomials degree at most 4? And that's our 1, x, x squared, x cubed, and x to the 4. And finally, we have, suppose V is a vector space and V has a linearly independent subset with a finite number of elements. True or false? V must be finite dimensional. Well, linearly independent, when we look at basis, our basis tells us our dimension. And here we have finite linearly independent set. And we have one property that's going to help us with this, and it's the dimension bound theorem. And it tells us that the number in linearly independent is less than or equal to the number in spanning set. And we need to be both linearly independent and a spanning set. And a spanning set will have more, at least the number of elements in our linearly independent set. So here we've said we have a finite linearly independent set. So there's a finite number of elements in our linearly independent set, but we haven't bounded above it. There's no reason why we can't have a larger linearly independent set. There's no information telling us there's an upper bound. So because of that, we have no bound on the size of the basis. If I told you a finite spanning set, every linearly independent set has to be smaller. We have a bound. Here, we don't have a bound. So as we don't have a bound, this would be false. There's no reason why we have to have a finite spanning set. We could still have an infinite spanning set.